So the navigation and observation data are stored in the receiver. So these files are normally captured and stored in the vendor's specific file structure, a binary file structure, but they are converted to Rhinex. And we have seen the navigation message files for two different GNSS systems. And now let's see the observation data for a location for at a given point. So this data file will include some observation or some measurement between the receiver and the satellite. So, for example, this information, this Rhinex file, again, is obtained at Ankara station for 2019, the 1st of January 2019. And this data, again, include the header data, you see. So the end of header means that the data will begin after, okay, the data collection will begin just after this line. So within this file, we see some important observation information. So the entire observation, for example, within this file for 24-hour period is included in the file. So before you have seen this, this was, for example, for the navigation message file, navigation data. So you recall G for GPS, R for GLONASS, and M here you see mixed. So this means this station can collect data from multiple systems, from several satellites. We will see, for example, here in the system and of the number and observation time section here, you see there are several systems. So G for GPS, R for GLONASS, E Galileo, C Beidou, J QZSS, and S, these are IGNOS system, European Union's satellite-based system. So this is also included. The Ankara station can also collect the data from, for example, from Astra satellite. This is the telecommunication satellite. It has an altitude of 36,000 kilometers, and they also send some some signals. So a limited number, as you see this, it is not so so detailed as the other systems. For example, the GPS system, if we take GPS systems, we can see in 4 blocks 12 types of information. So C1C, for example, if you look at the Rhinex description, which is provided in this week's repository, that C1 is, and here all C's, beginning with C's, denote the pseudo-range observations. So this means these observations will include in meter unit. And L, so what is in L included is the phase observations. So as you recall, phase observations are not scaled. So these are only the number of cycles within this information, beginning with the initial value whose numerical value is not known, and this phase cycles will be counted by the receiver. And the third, which in each block there are 3 okay, there are three numbers, and the first number code observations or pseudo range observations, second number phase observations, and the third is the signal to noise ratio. This is the value which is provided for some certain users, but we will skip this, okay, information within our lecture. So as you see, so this is first block, and the second block, it begins with C2. The number increases to 2, from 1 to 2. It is the first, okay, the first signal, and this is the second signal, which means that the carrier phase for the, okay, for the L1 frequency, for the first frequency, and carrier phase for the second frequency. So as you remember that the carrier layer is used for directing the satellites to the, okay, receivers. And carrier is the most precise of these of the most precise information is provided by this layer. So although this layer has no meter, okay, meter composition, and as you see for GPS, there are two more blocks, and within GPS, for example, three different carrier layer is used: L1, L2, and L5 frequencies. So these two frequencies, as you see, the same L2 frequencies, the information gained from L2 carrier, but the obtaining or the resolving the signal is realized by using different methods. That's why there are two same types of measurements here. And why do we use in these systems more than one carriers? It's because we want to eliminate the effect of the ionosphere. So the ionosphere is the most disturbing error source for GNSS positioning. For example, it may reach values so up to hundreds of meters. That's why these hundreds of meters is so important for GNSS positioning, because we want to obtain centimeter, even millimeter level positioning. That's why we need to eliminate the effect of ionosphere. For the elimination, we need at least measurement in two different frequencies. And as you see, in a modern GPS system, modern systems will include three frequencies or more frequencies, so that the ionospheric effect can be easily solved. And apart from the ionosphere, there is also one other issue: is the ambiguity resolution. So as you recall, the phase measurements include an ambiguity resolution and integer number of unknown. So that's why we need to resolve this number with high precision, because the resolution of this ambiguity will increase the accuracy of the positioning. That's why obtaining reliable numbers from the observations, or estimating the reliable ambiguity resolution, will increase the accuracy. So as you see, the systems will include at least two carrier frequency measurements. So for example, in GPS we have 5, not at all satellites, of course. At certain satellites, the newest satellites include the L5 observations. So and the other systems include these observations. As said, at least two carrier frequencies should be used in order to eliminate ionosphere. So with the elimination of the ionosphere, we will not make the concern within our lecture, but be aware that the using at least two two different carrier layer, so or the making observations by using two frequencies is necessary for the elimination. So as you can see here, the approximate position in Earth-centered, Earth-fixed coordinate system is all included in this, okay, in this file. So yeah, so you know from the surveying practice that you go to the field and measure the distance and angles, but before doing that you set up your instrument, and after just setting up your instrument you need to measure the height of your total station, so height of the of your instrument to a reference, from the point itself to the reference level. So in this same manner, we need to make observations. So for example, in the height, so there is 7 centimeters, and in the X and Y components, there is no offset. So this 0 means the instrument is just set up on the point itself in X and Y direction, as you see here. So, and the first observation, as you see here, begins 1st of January at midnight and ends at the next day midnight, so nearly next day midnight. So the observation interval, as you see, is 30 seconds, every 30 seconds. So the measurements will be recorded. Now, there are some other information, but we can skip for the time being. So let's describe so briefly what these lines, or at least for first of the observation block. So the first observation was taken at 1st of January at midnight here, this denotes, and there are 36 satellites observed. So be aware, 36 satellites. So G means the GPS system. So for example, for GPS system, we have 12 satellites. So this 12 satellites. And for GLONASS system, we have 8 satellites, 1, 2, 3, 4, 5, 6, 7, 8. It is total 20. And European Union's Galileo system, 1, 2, 3, 4, 5, 6, 7. That's in total 27. And Chinese system, 1, 2, 3, 4, 5, 6. So this makes 33. And one Japanese satellite was observed, and two EGNOS satellite was observed. In total, 36 satellites were observed at this very time. And what are the observations? The observations, as you see for GPS, there are 4 blocks of information. So this first block is the first layer. So the frequency 1, frequency 2, and frequency 2 again with other method. So the so-called Z tracking, you can refer to the Rhinex file description for this, and the L5, the third frequency. So now we find these in this order. So this is the first. Now you see this is the second, and this is the third block. So sorry, this is the third block, and the next one is missing. As you see, there is no the measurement with the L5, because the L5 is included for GPS system only for the newest satellite. So you see this satellite is newer than the satellite 5, for example. And the first one is the pseudo range measurement. So you see here these measurements are here. For GPS, for example, these are all pseudo range measurements, and these are in meter unit, as you see. And you can see, for example, is nearly 21,000 for G21 satellite. So it's so close to the Ankara station, to the antenna or to the receiver, and the farthest location for the satellite is G13, for example. It is around 26,000 kilometers. So if the distance increases, so this means the satellite is around the horizon direction. So it is either in the setting position, or it is newly rising position, or the ascending or descending positions. So the shortest distance will be around the zenith direction, for example, here. So G20, G21, so or G26 around the zenith directions. And the second information here, as you see, the second information for GPS satellite is GPS satellites, the 12 GPS satellites are the phase observation. So these numbers are initial numbers. So these denote nothing. So these are the so-called street numbers. So it means nothing. They mean nothing for the time being. So if you turn on your receiver, so these numbers will be automatically counted, and it begins the receiver begins to count, to track the satellites and count the phase cycles. And the third observation, as you see here, is the signal to noise ratio. So this the further description will be omitted here, but the best number here, or the lowest number, would be around 38. So beginning from 38 up to 50, 52, 55, for example. So this means the observations are quality observations, and the lower values, lower than 30, 38, so means that we have some problematic issues. So, for example, the satellites around horizon will, in general, lower values. So, for example, 39. So, satellite close to the zenith direction, for example, you see here, will have larger values. So you see 30, 49. So again, so 25,000 kilometers. Okay, you see 39. So this may be used as the the signaling of the satellite's location. So this number is also dependent on some other atmospheric, especially ionospheric conditions. So this is a sign of the signal quality. So this is the second block you see, and this is the third block. So and for other satellites, the same order. For example, for GLONASS, the last block will not be seen in that case. So here, if you go for example, for GLONASS system, you will see no. Okay, so here you will see no information because it includes only 3 blocks. So as this is the description of the observation file. So within this observation file, the satellites or the antennas capture the signals, and the receivers demodulate the signals into the navigation and observation file. And within the observation file, we include the pseudo range observations and the phase observations. Now in the next video, we will try to determine our position by using the observations here for certain satellite system, for example, for GPS, by using pseudo ranges. The so-called point positioning algorithm will be applied for the determination of the satellites or the receiver's position. So the receiver position is here given in 3 components, but this is an approximate position. So this information can be used for the linearization of our nonlinear equation.